Brini from Imperial and Seifert-fibred. And after Andrea's talk, we have a rather long break, and Pavel Putrov agreed to maybe answer some questions, and maybe we'll have an informal discussion on some of the subjects of his work with Vafa and Gopakumar. So right after Andrea's talk, we'll take a little break and then reconvene for informal discussion.
Thank you very much. Is my voice audible? Yeah. Yeah, the previous speakers have set the bar pretty high when it comes to try and make a bilingual talk. I'll try and do my best to match up with what they've done. So just before I start, let me just give you a sort of summary of what the main thread will be. Is this blackboard visible? Yeah. So the sort of take-home message of this talk, mostly for mathematicians who may have heard this today for the first time, is that there's a triangle of rather stunning relations linking topological invariants, quantum invariants. And is this legible for people at the back? Complain vigorously if not.
Yeah, yes, good. That's good.
Doesn't work.
Oh, it's not
turn
working,
it on.
but we can hear you.
All right. Better? No. All right. Quantum invariance of real three-dimensional manifolds with some various curve counting theories of manifolds in complex dimension 3. Enumerative invariance Gromov Witten, Donaldson Thomas of Calabi Yau trees. And third character in the play will be a sort of mirror symmetric, well, in a precise sense, a mirror symmetric version of this counting theory up here in the form of periods and, well, higher genus generalizations on, well, threefolds or onefolds, in fact, over C. So that would be sort of a classical statement of mirror symmetry and its higher genus variant by BCOV, and in my precise context, this will take the form of the celebrated topological recursion of Eynard and Orantin. And so if I can make some physics closed captioning, so there's a topological A model on these backgrounds, this topological B model. And as we all know and love, the top left corner is a topological gauge theory, Chern-Simons theory. So my plan will be to give a motivation that assumes no prerequisites, in case you literally never heard of any of these guys, that will serve as hopefully a good introduction. And then I'll describe, hopefully it will give a good sense of all the arrows, if not of the individual vertices. I will describe how the Gopakumar Vafa correspondence in the case of the three-sphere fits in this game. And lastly, we'll discuss how this, so who will occupy the spaces in that diagram in the case of spherical free manifolds, and how you can go about proving these arrows. Yeah, let me start with one. So the baby example is in 0 dimension. And this is just a gate Gaussian matrix model for UN matrices. And what this is just, well, you take the Lebesgue measure on Rn squared, the Lie algebra of UN. with a Gaussian weight. I'm actually going to vary a bit the Gaussian weight in here. T is in R plus. And I want to normalize this, in fact. The first G of gauge stands for the fact that I normalize this measure by the volume of UN, so the canonical total mass of the R measure given by the canonical normalization for the Killing form. And I want to compute the log of this. And so this is a sort of logarithm of the expectation value of 1. I could have considered like the log of the cumulant generating function or some formal parameters gk, trace m to the k. This would be the connected correlators. So the task is to study this guy when the rank grows big. So the Gaussian integration is trivial, and this volume is as well a known result from the early 80s. Probably even earlier, this is just a product of volumes of spheres. So it's an exercise in the Stirling asymptotics to compute this logarithm. And there's a leading term that I'm not going to tell you what this looks like. Well, I could, something like this, order n squared log n, in fact, log t. I'm going to bury also the finite order 1 term as n grows big, and I'm going to focus on the subleading corrections, n2 minus 2g. So these are in even powers of n, and the asymptotics is governed by Bernoulli numbers, p to g, 2g, to g minus 2. I would like to attach to this rather simple integral. If you want the simplest ever gauge theory, you can consider gauge theory on a point, pre-gauge theory on a point, a pair of geometric objects of rather different flavor. So I'm going to just make a couple of observations. Observation A, so this is related to the topology of the moduli space of curves, mg, and it's the limit for compactification with mark point, mg1 bar. And the observation is that, let me call this fn of t, fn and t, is that purely in terms of acronyms, this gauge Gaussian matrix model is the same thing as, at least at the level of the partition function, and with some adjustment of parameters, as an ungauged doubly scaled Penner model. This is Penner and Distler Vafa. This latter paper in the early 90s. And roughly the statement is that if you consider just the standard Gaussian perturbation theory for this ungauged model, it organizes itself as a sum of ribbon graphs, connected ribbon graphs, weighted by, well, what I'm saying is not specific to this matrix model, of course, for any matrix model. So let me not be not specific about the weights that are assigned by this acronym to the diagrams for the moment. And by the Strebel-Haber correspondence, to each of these guys we can attach a simplex inside MG. This is actually a sum over G and over simplices, let me call delta, simplex in MG of, well, n to the 2 minus 2g time, okay, some weight attached to the simplex. And I'm being incredibly vague about what these weights look like, but the only thing that matters at this point is that this Penner specialization is tantamount to attributing to each of the simplices exactly -1 to its dimension. And moreover, the symmetry group of the graph matches exactly with the stabilizer group for the mapping class group in here. So the answer to that is that this takes the form of a sum over G and 2 minus 2G, the other characteristic of MG. So the sort of simplest example of a topological A model. So let me call these guys FG. And this equality, say A, should probably erase it. So the FG is equal to chi n G. This is in fact the famous theorem by Haber and Zagier. And the second observation that I would like to make, so observation B, is, again, I want to attach to this integral a geometric object, but of a quite different flavor. So that would be actually a spectral curve. And if you've heard about this before, the topological recursion. So in plain words, just this, we could say that the steepest descent analysis of the gauge fixed form of the matrix model in the eigenvalue basis gives rise to what can be codified, at least at the, that's two implications. So genus 0, we have that there exists a family of polynomials, x and y, and in fact, for this particular case, this takes the form of something quadratic in y and x. So in fact, a family of plane curves such that the planar free energy can be recovered in terms of periods of a meromorphic differential on the Riemann surface defined by this equation. It's like 1 over 4 pi I. There's a basis of periods in a completely supported homology of this Riemann surface that yield the leading part to start with. This was something that was buried in the cube, but what's remarkable is that for genus greater than 0, there's the full set of FGs can be recovered through the so-called topological recursion of Eynard and Orantin applied to the spectral curve stuff. And as a matter of fact, this is not a recursion in the free energies themselves. It's a recursion that involves the connected correlators as well. So as a byproduct, these are recovered too. So the correlators are recovered as intermediate steps in this calculation. So in the physics lingo, this is the this is possibly the simplest example of a large N gauge string duality, and in both cases it takes the form of so these letters A and B match with the letters A and B that appear in this diagram up here. In particular, this describes the topological A model on a singular conifold, or equivalent to the C = 1 string as self-dual radio, and this would be the topological B model on, again, the singular conifold, which is its own self-mirror. So the physics side of it is like A model on singular conifold. This is not visible, is it? Ah, okay. On conifold, and this is the B model. Now, why does this have any relevance at all for the topic of this workshop? Is that this is the simplest instance of what goes on in a sort of most basic case for the theory of quantum invariance. So the non-baby example that I'm going to consider. So, yeah.
So in this F, n comma t.
Yeah.
Does that weight also involve n's, or does it depend on t only?
Sorry, you mean the FG using here?
On the right hand side, the weights associated to delta or gamma. Function of t alone, or is there also?
No. So here I was being a bit sketchy. So this is something. This bit here of the formula is something that is shared by all one matrix models. If you specialize to the Penner matrix models, these guys are just some specific numbers. And to be more precise, the n here is related with a rescaling that involves t to the n that I've written up there. But otherwise, with this identification, the identity carries through. Yeah. So the next example. So what will be the main example? Three-dimensional. Is the case of three-dimensional. Is the case of Chern-Simons theory. UN Chern-Simons on a manifold S3, and possibly with the unknown, just to start with. Now, in this case, this sort of Q deformation of the case that I've just described. So consider formally a path integral in a space of connections small gauge of the QFT with a weight given by the Chern-Simons functionals of A itself, and possibly the role of correlators here will be played by the colored version of the Ohmslian invariance. So this would be expectation values of characters in some representation R of the holonomy around the knot, in this case the unknot, of the connection A. And the way this is extended to this case, well, we know what the Witten Reshetikhin Turaev invariant looks like for the case of S3. Let me just start from the partition function. Fn and k, let's say. Again, this is going to have some leading part in order n squared, and the sort of interaction that this receives will be in the form of the polylogarithm of order 3 minus 2g of e to the t, where t here is 2 pi I n over k plus n, and gs is just t over n. Now, before we had a pair given by a moduli space of curves and a family of spectral curves with Eynard Orantin recursion that captured the whole tower of higher genus corrections to the large n asymptotics. Oh, sorry, there's a logarithm here of this free energy. The question is, what do we put now here and up there? Now, the insight of Gopakumar, Ooguri, and Vafa in 98-99 was to, well, in this case, one does not deal with a topology of the moduli space of curves. It's actually the virtual topology, virtual intersection theory on the moduli space of stable maps. Moduli of maps is on Calabi Yau threefold, which is given by the total space of two copies of the tautological on P1, the result manifold. And just let me erase here. And the sort of the generalization of the Harari-Zagier formula in this vein is given by the fact that the coefficient of order e to the dt of this fg of t is exactly the unpointed genus G degree D Gromov Witten invariant of X, just the degree of the virtual fundamental class for this Calabi Yau threefold and this topological data. And does that picture carry through? And well, it does, again, almost verbatim. In this case, we can bypass a direct steepest descent analysis. We could, I mean, it's been done. But one quick way of guessing what spectral curve setup would be relevant for this case is just to realize that this is a non-compact toric variety. The fan is a cone over this picture. And by general principles of what the planar B model is, so at tree level, the mirror could have probably kept this. So at G equals 0, we're going to have the same period relations as before on, again, a family of spectral curves, PT of e to the x, e to the y, where PT is just the Newton polynomial of that polytope. So it's just 1 plus e to the x plus e to the y in C star times C star plus e to the, say, t plus x plus y. And at higher genus, yet again, the FGs are recovered as the Eynard Orantin invariants of PT. And now if we throw in knots in the picture, and in particular the unknot, this would give rise to the Humphreys for the unknot. Well, in physics the color Humphreys. In physics normalization, can be translated into a count of open Riemann surfaces with a Dirichlet boundary condition on some Lagrangian in X. And as before, the B model statement for the correlators states that the intermediate invariance from the recursion will give, in this case, the knot invariance for the unknot in with arbitrary coloring. Now, yeah.
What are the colorings here, or how are they related to G? Or, I mean,
So I think I'll erase this. So there was a trace in our representation of the holonomy at some point. So when I wrote it, probably
okay,
yeah.
so that's suppressed from the notation everywhere.
Yeah. So I could put a representation here. So in fact, the correct statement is if you take the connected part of expectation values of power sums instead of taking Schur polynomials in the eigenvalues of the holonomy, the exponents of the power sums would match with the windings of a stable map from an open Riemann surface with boundary and Lagrangian, and the individual wrapping number would be the exponents in the power sum that you picked.
What is G on the left hand side? I mean, what is?
Yeah, right. So in here, I'm considering.
No, I mean on the left hand side. What is? Or
Right. Yeah, this guy is expanded in a large n. So this guy depends on n. Right. So I'm taking.
Or e to the n or something. Okay.
Yeah, and I'm taking essentially the 2 minus 2g plus h coefficients of his 1/n expansion for this connected correlator. Sorry,
Can you
didn't
explain what's the difference between the topological recursion and the first line where you were just...
None. The one you mean the one that I've written for the Gaussian matrix model, and the one that I've written for the mirror of the result conifold.
So,
So
the top line, which was for S3, and then the bottom line, which was for the Humphrey polynomial, the unknown. So
Right. Okay, so as I said, so the topological recursion is a universal calculus of residues, which works in the following fashion. You feed the algorithm with a family of plane curves and the marked basis of symplectic one cycles on a curve. And there's a recursive way of reconstructing the free energies starting from just that data, so just from the form of the PTs. The intermediate steps, so this is not, as I said, this is not a recursion on the free energies themselves. You cannot reconstruct FG from knowledge of the prior FGs. The recursion takes into account all the connected correlators with some bound in the powers. So there's this extra index GH that I put in here.
Okay, so what is the extra index doing? What is
Okay. The extra index, so when I wrote the cumulon generating function, essentially you're going to compute things like averages of traces, say in the matrix model case, of things like that, or maybe, multi-traces, Z prime minus n, and you take the connected part. So the number of traces that you put in here is this index h that appears, and so these are called the Arrel-Zagier functions in the case of the Gaussian matrix model. More correctly, they're Laplace transforms. And essentially, from the knowledge of the free energies and the correlators at some order in their 1/n expansion, and with some number of insertions of these traces, you can recover the FGs at any order. So the EOGH are the expansion at the fixed power in 1/n of an endpoint correlator in the matrix model, if you like. Right. So now, this has been used in various ways, and especially in two orthogonal ways. One is as a sort of building block to consider more generalized, more general Calabi Yau 3 geometries, out of which you can extract Gromov Witten or DT type invariants. The Gromov Witten picture is the one that is appropriate to this type of discussion, most notably in the theory of the topological vertex. And the sort of B-model counterpart is an extrapolation of the Eynard Orantin recursion for general mirrors of toric Calabi Yau 3s, giving an unambiguous way of computing topological string amplitudes on these backgrounds to all genera. The other direction that one could take in the story is, well, instead of using this as a building block for more complicated examples, I'm taking the building block seriously, so this correspondence seriously, and I would like to refine it. So there's a whole bunch of ingredients that can be varied in this setup. So why not modify them? So the quest since 1999 is to generalize this picture to, well, one is the topic that is probably at the heart of this conference, so refined invariants and the category 5 version. This is a point of view I will not have anything to say about until about 5 minutes to the end of the talk. Another direction is, well, you can replace the structure group of Chern-Simons with some other classical gauge group that allows for 1 over n expansion. And correspondingly, for example, the Kaufman polynomial, the sort of most impelling need for some has been to replace the unknot with a non-trivial knot. And the situation here is fairly well understood in the case of torus knots, and there have been proposed far-reaching generalizations of the setup for more general knots, where at least spiritually all ingredients, including the topological recursions, should carry through. And what's perhaps well, one of the trickier things, well, this is probably at the same level of difficulty as the third line, is replace S3 with an R3 manifold. So this is a point of view that has been a problem that has been posed in the case of land spaces, posed and solved by Aganadic, Klein, Marinho, and Vafa in 2002. So the idea would, the problem would be if you start with a quantum invariant for some, say, the real projective plane, so a real three-dimensional projective space, or some rational homology sphere, can you attach to that a Calabi Yau labeled by that choice of 3 manifold and the family of spectral curves such that the Gromov Witten theory of that Calabi Yau and the spectral curve on its spectral curve mirror would yield the 1 over n expansion of the quantum invariant and would reconstruct it unambiguously. And if you want to include knots in the picture, you need to also single out a Lagrangian on this Calabi Yau 3. So today, I'm going to give the answer. For the case in which 3 is positively curved. In particular, M3 is the quotient of S3 by the isometric action of a finite subgroup of S4. So, yeah. Any questions? Right. So let's start from A. So who would replace the result conifold here? So just to remind what the story was in that case. Now, Well, in general, the open topological A model on the cotangent of M3 would just give the Chern-Simons theory on the zero section. And so let's start with a cotangent. So essentially, let's pursue the same path that was considered in the case of the Riesel conifold. So for the cotangent of the unit sphere S3, well, this is isomorphic. This is a Lie group, so it's parallelizable. It's just R3 times S3. I'm going to put a complex structure on this by realizing that as the space of 2 by 2 matrices with unit determinant. This is just a polar decomposition of a 2 by 2 matrix, which sends, well, the angular part to S3, which is special since this is determinant 1, and the polar part to R3, which is traceless, since the determinant is 1. Now I want to vary this picture, as was done in the case of the conifold transition, by considering, well, a family of algebraic Calabi Yau threefolds over the puncture disk. Let me say over C star, given by the determinant map on GL2C. So just the fiber over a point mu greater than 0 is just T star of S3 with volume mu. And I can partially compactify this picture by adding the central fiber. So if I do the same for general 2 by 2 matrix over C, the fiber over mu equals 0 when I've collapsed the base 3 sphere. So let me call this X mu. So X0 will be just a vanishing locus of quadratic polynomial of this one. And, well, the toric minimal resolution is taken by considering X hat 0, which is just a pair AV in M2C times B1, such that A V is equal to 0. The resolution morphism is given by the projection on the first factor. So this is just a minimal resolution, the small blow up of the conifold singularity. Now, if I play the same game for, say, the Poincare homology sphere, well, anything that is, so just an orbifold of this picture, just a quotient of this picture by gamma. Let me I should append a label gamma everywhere. So I guess I have S gamma in here. And then I have a gamma action. So the gamma action is, so let me, for the time being, gamma will be a central extension of a left acting finite subgroup of SU2. So these have an ADE label. So gamma in here will label just one such thinking diagram. And if this guy is left acting, I'm going to have a left gamma action on this A here, which leaves untouched the V coordinates. So in particular, this action covers the trivial action on the base B1. So some remarks. So many things are well defined, also mathematically. The first is a rather trivial remark. It's the thing I've just said. And this the gamma action for these ADE cases is fiber-wise. The second remark is that there's a two-dimensional torus action acting on x0 mod gamma hat mod gamma, which is given by we have a fiber-wise quotient of O minus 1 plus O minus 1 over P1. The scalar action on the fibers descends to the quotient, and then we have a C star action that rotates the base. So in particular, it acts on this with compact fixed loci. If you're a string theorist, there are two distinguished chambers that where you can consider the A model on this target space. One is the orbifold chamber, where we have one geometric modulus for the base and a number of twisted orbifold modes for the orbifold action. And the one is the large radius chamber, where essentially we consider the theory of maps to the fiber-wise resolution of the singularities of this guy. And that would create a chain of P1s with intersection matrix given by the Cartan matrix of the algebra corresponding to this Dynkin diagram. So in particular, we can define by localization Gromov Witten invariants of x gamma at all genera in both phases, both the large radius and the orbifold one, which is the one relevant for transassignments. And moreover, we can, since there's a resonant subtorus in here that preserves the Calabi Yau 3 form on this guy. This is the one that will be used for localization, and it's a crucial ingredient that Katz and Yu used to define an open counting theory of maps with some canonical Lagrangians. In particular, you can construct canonical Lagrangians for all these gammas. And define at least from the operative point of view, an open Gromov Witten theory of genes G, H hold stable maps to X gamma with boundary on L gamma. And well, there's a further remark would be that this Signe-Vafa orientifold action that led to the SO-SP theory carries through to this setting, since the generators commute with all gammas.
They correspond to unknowns.
Sorry?
The Lagrange.
Right. They would correspond to invariants of fiber knots around any of the. So these are Seifert-fibred free manifolds. In the D and E case, you would have 3 exceptional fibers, and invariants for knots running along those fibers would match with this open Gromov Witten counting here. So things can be constructed, they can be defined, they can be computed, but before I tell you about this arrow, the horizontal arrow, let me define what the B model counterpart will be. So can we construct a family of Riemann surfaces with 2 marked meromorphic functions such that if I compute periods of this meromorphic differentials on the curve, they give me the planar free energy, and if I plug them in the Eynard Orantin recursion, they reconstruct the all-gens asymptotic of the quantum invariant. And this is what I'm going to do next. B side. Now but the remark 2, well, the fact is, except for type A, so the case of length spaces, this 2 torus action does not extend to the full 3 torus action on this variety. So this variety is, so by R2, x0 hat mod gamma is non-toric. So in particular, we have no direct way to apply the Hori equal Vafa mirror, just taking the Newton polygon, the Newton polynomial of the polygon given by the fan of the historic variety when gamma is non-abelian. So for type D and E, we will need some other means to construct the spectral curves. And the way out of this conundrum came from R1. So essentially, because the action is fiber-wise, a family of spectral curves can be computed from geometric engineering plus the Seifert-Witten integrable systems correspondence. So by the standard law of geometric engineering, a type 2A compactification on a background like that would give some theory, but some gauge theory with A supercharges in 4 dimension with gauge symmetry specified by the Dinkin type of this diagram, and no adjoint hypermultiplex since we're fibering on P1. So by the geometric engineering will tell you that a limit of the Gromov Witten potentials, the generating function of Gromov Witten invariants for this target would give rise to gauge theory prepotentials in 4 dimensions. And
do you not lose something when you take that limit? Do you not lose something when you take that limit?
You do. So what that tells you is that essentially there's a divisor at infinity in the extended stringy Kähler moduli space where things look like as they live on a curve, which is a Seifert-Witten curve or something. And that something, well, something that is very well known for the classical case, and even in the exceptional case, you know that this is a spectral curve of some integrable system. The Coxeter generalization of the periodic to the left is. But in fact, even if you stay away from that divisor, things still have a gauge theory interpretation just in 1 dimension higher. So this prepotential will actually be prepotential for a 5-dimensional theory on our 4 times S1. So the sort of idea is to go down to consider 5-dimensional n equals 1 super Young mills on our 4 times S1 with gauge group. The gauge group specified by the Dinkin label of the singularity. And to go from here to here, we use the Seifert-Witten integrable systems correspondence. This extra 5th-dimensional circle has, so this deformation away from the divisor that you were mentioning has a clear meaning from the integrable system perspective as a relativistic deformation. So the claim is that the 1-folds that I'm looking after are the spectral curves of the relativistic total chain of type gamma, and which is what I'm going to describe in 5 minutes. So the sort of kinematics that is underlying is driven by the split algebraic torus of dimension twice the rank of the algebra attached to the Dinkin diagram, and with a Poisson structure which is logarithmically constant, xi, yj. And it is given just by the Cartan matrix of the algebra. Now the dynamics is pulled back by a Poisson immersion of this phase phase space P to some distinguished cell, symplectic cell, in the group, the complex group of ADE type gamma, we call it G gamma, mod the Poisson action of the Cartan torus. And since ad-invariant functions are in involution with respect to the natural symplectic structure that we have here, it comes from the Drinfeld-Jimbo R matrix. They pull back to Hamiltonians in involution on P. So let me fix, say, fundamental weights rho I for the algebra, and I just pick traces for L. Now I can compute spectral invariance by fixing well, any irreducible representation for the algebra. It makes sense to take a minimal dimensional. We call it P toda of rho. Rho is just an irrep for G gamma. So this is the characteristic polynomial in representation rho of this map L. And well, this is actually a polynomial just by expanding the antisymmetric traces of rho in the fundamental characters of L in H1, HR gamma, and X. Now this is not yet a spectral curve, but what's relevant for gauge theory is not the theory that comes from a simple Lie algebra, simple Lie group, but rather the affine extension of it. So going from G gamma to its affine counterpart is tantamount to taking a deformation of this map by a spectral parameter. And in particular, spectral curve is given by sending G gamma to its affine counterpart, which is tantamount to sending L to some specific deformation given by an extra parameter Z. Now, the vanishing locus, P rho toda, of H, X, and Z would be my spectral curve. This is something that can be constructed entirely representation theoretically. All you have to know is to fix a representation. It turns out the prepotential will not depend on the choice, so you can just as well take the minimal dimensional ones in all type ADEs. Compute the decomposition of the fundamental of the antisymmetric characters in terms of the fundamental characters, and compute this deformation by the spectral parameter. Just these two steps. Once you accomplish that, you have a candidate. So you know what you have here. You got a non-compact Calabi Yau 3 with some Lagrangians. We got a family of spectral curve here. Is there something that we can actually prove?
And this is all still for gamma, which is in SU2 of SO4.
It's in SU2, but going from SU2 to SO4, at least at the level of the partition function, consists of multiplying by a constant factor, which will give you an unstable term up here. This would be a sort of genus 1 degree 0 Gromov Witten invariant. So there is no counterpart for the changing and going to, say, the left-acting binary icosahedral group and its trivial central extension. So let me just give a proof. of the vertical direction, and this is the content of various papers. Sort of ancestor is a paper with Eynard and Marino. There's a paper of Gaetan, Borot, and Eynard, and this was finally completed in a paper of Gaetan and mine. So just the main points in 5 minutes. The way the proof goes is that the Reshetikhin Turaev invariant, the Chern-Simons partition function, is essentially a matrix model. It's an eigenvalue model with some measure. This is an inset of Marino that it actually holds for any homology sphere, and for gauge groups more general than UN. And it's a close cousin of the Gaussian matrix model that I told you about at the beginning, in that, well, if you go to this gauge fixed form, where the measure looks like, well, an integral over eigenvalues, but a square over Vandermonde, and Gaussian one-body potential. The only thing that happens when you consider homology spheres is to have an integral like this, and you deform the Vandermonde by sending it to some product of Q-deformed Vandermondes with hyperbolic measure, and with some coefficients that will keep track of the surgery data that realizes your Seifert-fibred manifold. And if you do this, you can do the steepest descent analysis for this matrix model, and the answer is that the planar resolvent, which is one of the marked meromorphic functions that I'm looking at, and for the spectral curve, so the y of x, is never log algebraic itself. So there is little hope of extracting algebraic curves from here, but in all these cases there is a symmetrization, which is very natural. There's a symmetrized resolvent, which has the same discontinuity on the physical cut for this y of x. So it extracts the same planar free energies, and what it enjoys, so let me call it y sim, is that for all types ADE, so for all gamma, there exists a polynomial. So this is log algebraic. PCS with integer coefficient, and it's a function of some variables, the first moments of the distribution. These are in one-to-one correspondence with the Hamiltonians that I was mentioning before. At e to the x, e to the y sim, such that p of x, y sim of x is equal to 0. P Chern-Simons. So we have a family of spectral curves, and moreover, you can prove that the constraints on the form of the partition function, sort of Schwinger Dyson word identities that you can write for the matrix model, are solved by the topological recursion. Now the question is, how does this family of curve relate to that? And a priori, they could differ. It's an everyday experience for people doing topological strings, that dealing with different backgrounds that give the same content in terms of amplitudes. But in this case, we're lucky. We get an on the nose p toda gamma. This relativistic toda gamma is the same as p Chern-Simons. And let me append the subscript gamma for all gamma as a result of the steepest descent analysis. And Now, as I said, the recursion is just a set of universal formulas that just depend on some initial datum is the form of these polynomials, a choice of one homology cycles, and that's it. Now, the recurrence is the same. If you want the fact that the Eynard Orantin recursion gives the higher genus topological B model is either a definition if you're a mathematician or a consequence of the two-dimensional reduction of the Kodaro-Spencer theory. If you're a physicist, the recursion is the same, the starting point is the same, everything is the same. So in particular, this implies an identity at all orders in 1 over n, all degrees. So, and because the recursion involves this extra winding variables, which is what is mapped to colorings, all colorings. And now one problem that was raised in the first talk in the morning is how does the story of finding large n duals beyond the case of spherical manifolds can be tackled. Now, one sort of no-go theorem that we're finding here is that in that case, you can prove that there is no such symmetrization that will give you an algebraic curve. So there ain't no way you can write down some resolvent, but that resolvent will not be something that comes from a family of spectral curves. You cannot write the dual for that, at least on the B model side, as ZW equals polynomial in two variables. So you're probably parting ways with algebraic geometers in that setting. And in -1 minute, what about refinement? There are some avenues of attack of various problems that can be opened by this setup. So for each, in particular, the refined version of the holomorphic anomaly equation is something that can be used to compute the set of invariants that themselves depend again on a choice of background flat connection, as they did in the first talk of the morning. And at least for a closed string sector, the refined holomorphic anomaly equations studied by Klein, Walchert, and other people can be applied to this sort of 5-dimensional gauge theory setups. Moreover, the fact that you have a quantum, an integrable system gives an open, in this particular setting, gives you access to their quantum counterpart, which will give you at least a glimpse about what happens for 1/2 of the omega background in the case, at least in the direction where you're pushing your quantum parameter. From down here, the extrapolation of the blow-up equations in the context of instanton counting to the exceptional root systems will also allow you to compute refined invariants for, say, the Poincare homology sphere at large n. And 2 months ago, there is no, what I've discussed about localization in orbifold Gromov Witten theory has nothing to tell you about refinement from up here, but it has been argued that even for the non-toric cases, there's a combinatorial adjustment of the usual refined topological vertex. Well, a couple of months ago, paper by Omori et al. That will give you a third avenue of attack of computing large n refined invariants for this class of 3 manifolds. That's all I wanted to say.
So when you include the links and knots and all instead of knots, just more variables, then it turns out that the curve is replaced by a higher number of variable cases. So
right.
And in that case, have people tried to develop the analog of techniques of Eynard Orantin? Or
no, I didn't, but Clem did a couple of years ago.
So has that been applied to your problem?
Well, my problem doesn't.
If you consider not just the unknot or whatnot, if you include interesting knots in length space or just quotient.
Well, in this case,
not knots. I mean links.
Well, in this case, you have the knots. You have the knots for free.
No, knots I know, but links I meant. More than one.
Yeah. Well, I think some of them you probably know how to.
Then did also the links? I didn't know that. Is that true?
No.
Knots. I think he was. Somebody has done links.
No. Just for the torus knots case, I would know how
The
to do.
strange thing about that link case is that dimensional things could be more than 3.
All right.
So it's not a reduction of Kodaira Spencer, but we know there should be a story. So that would be very interesting to actually see what it is.
Yeah, just for a torus knot case, I would probably have an idea. I mean, there's this. Yeah, but you have tricks in a torus knot case to consider the case of links.
Something more general and topological string. That from that perspective, it suggests that there's some interesting topological string version which is not just one-dimensional, could be n-dimensional.
Probably one could consider links colored by the same representational components.
Any other questions?
What about non-torus knots? That is possible.
I'm sorry.
Non-torus knots?
No, what this doesn't have. I mean, the answer can be yes, as soon as you consider something that is not a length space. So the class of knots that are covered by this construction are, as was said before, the fiber knots along the exceptional fibers of the Seifert-fibration, and those are the only ones whose quantum invariants can be written as averages of some matrix model. So those are the ones that are intercepted by, that are captured by this construction, and more or less, well, it's probably not a surprise, depending on where you come from. It can be surprising or not that this can be related to some class of integrable systems and the recursion.
But a naive question, which is just, so do you expect that this story will generalize any further, or is
well, not in this form. Not in this form. What I was saying is, it will not take the form of you got a nice integrable system motivated spectral cut that does the trick. So that's kind of surprising from the matrix model point of view, because that picture carries through, and the perturbation theory is exactly the same. The only thing that changes is just that the coefficients of the surgery data change a little. I mean, if you do sigma 237 instead of sigma 235, you got exactly the same diagrams, and with just some numbers changing. You do just Gaussian perturbation theory. It has all these nice extra U1 symmetries that you would need for all the I mean, the things that were mentioned in this morning. But I think probably some. I mean, the open A model on T star M would still be there. It's just that you're probably parting ways with algebraic geometers, both on the A and the B model side. So I don't think. Well, I don't know. This is actually a question that I should ask the audience. If I take the T star, the total space of the cotangent on a general free manifold, can I always give it a complex structure such that this is a Calabi Yau beyond the spherical case?
Yeah, no, you can.
You know, for all.
Of course, you can just study the local neighborhood of the M.
No, but that's a smooth statement. I was specifically asking about it was
there may not be a complete geometry if you're asking.
Yeah.
But that's not necessary for the A model.
Right. Yeah. I was with a head on the result side in a sense. So can I find an algebraic threefold? That's large.
That's the reason that we are not expecting.
Yeah. I probably.
If you count scalar parameters of what you're supposed to get, right, then it should be one for each free homotopy class in the 3 manifold.
Correctly.
If you take RP3 connects.
Oh, absolutely. Yeah. That's absolutely true. So of course you cannot expect this to hold in full generality. But for example, you can ask, what about the LMO invariant? What if I consider a case where I just restrict myself to the triple connection? So I got just one parameter, and I got a bona fide invariant on the 3 manifold side, and this has a matrix model interpretation. Is it too much to ask to have? Well, the point is, for people dealing with this topological recursion in matrix models, the typical experience was whatever matrix model-like thing you had in your mind, you would typically find a solution in terms of topological recursion on that. This does not seem to be the case for even for Seifert homology spheres that are non-spherical, and even for the LMO invariant for which you know that you have a matrix model. It's actually a single cut matrix model. It's a pretty innocent looking object. But the large N theory is kind of more involved than one might think, at least from that vantage point.
Thanks. Let's thank Andrea.